Like cheese.
Okay, so we're doing rotations. Rotations, as you know, we're talking about extended objects now, not point particles. So two concepts that are related, and it can be confusing because they seem kind of similar, but they're very different, are center of mass and rotational inertia, also called moment of inertia in technical terms. You can talk about the mathematics of what a moment is, but intuitively they think it's a rotational inertia. So we'll talk about that in a second. Just as an introduction, we need a little concept of center of mass, and then I'm going to do that after we do our energy analysis for rotations, because then we'll talk about torques and balancing and things like that, and we only need a little more with center of mass. Also, we're going to set up integrals in physics. So in physics, you need to, and engineering, you need to often set up an integral for your situation. And so we're going to do that just for rotational inertia first, because it's a little simpler integral in some ways. And you get the sense, and then in general, when you get onto electrostatics and a variety of other things where you set up integrals, you'll get the basic idea. And the basic equation will lead you into the specifics of the coordinates and so on. So first off, center of mass is an average position of mass, right? It's often obvious, and so we're going to start with that. It's the balance point or line. And again, we'll do more later. So if I look at something, I don't know exactly where that center of mass is, but I could probably find it if I could find the balance point. It's somewhere in there. If I could find the balance point, then that center of mass would be kind of in there. So I can see that a little bit, and I can play with it. A little bit delicate, right? The center of mass of this object is probably right here, but it's also halfway in probably. This is what we call uniform density. Uniform distribution of mass is a phrase that's good to use. Uniform distribution of mass. It's probably right there somewhere in the geometric center there. And I can, of course, balance it like this if I want, and that's easy. This now has a center of mass, well, some here, some there, so the average would be there, here, 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 here. The average will be there. I can't really balance it that way, but I can balance it like this, and we'll look at the force of gravity. And we'll be able to treat the force of gravity on the whole thing as effectively acting on the center of mass, even though there might not be mass there. And the center of mass of an object, the average position of the stuff, can change as an object moves, right? And so your center of mass actually is not a particular point because it changes as you move. We'll get into things like that. But basically the center of mass, because the thing that we need to know is that the center of mass motion, it would be like this, and I can use my old 1/2 mv squared, or I can use my kinematics. And then I can have rotations around that center of mass. And so we'll need to do that. If I throw this in the air, it could be rotating. So the point particle model of a projectile could be applied to the center of mass, and then we've got rotation around the center of mass that we need to add to the description of that thing. Okay, so lots of objects with center of mass, and we'll talk about that later. So the next thing we've got is rotational or moment of inertia, I usually. It's the resistance to changes in rotation. So it's inertia. But we'll find it doesn't have the units of kilograms or grams or slugs. So let's see what it does have. First, it's the resistance to increasing round and round rotation, omega. It's the resistance to decreasing. It's also the resistance to changing the direction of the axis of rotation. Okay, so if something's spinning like this, and then I want to make it spin like this, that can be like something spinning here. I can speed it up. How much does it resist? I can slow it down. If it's rotating, I could try to tilt it so the axis changes. But no matter what's happening, it has that resistance whether or not I try to speed it up, slow it down, or turn the axis of rotation. So it has that rotational inertia. Okay. However, the rotational inertia around different axes will change. So, or is different, I should say, excuse me. So you could feel this, and you can actually feel the rotational inertia. You can go, hey, how hard is it to speed that up around that axis? And here's another axis here. Go like this and see. How hard is it to speed it up, or how hard is it to slow it down? It's going to have more resistance to speeding up, slowing down, or turning if somehow I move it out farther away from the axis. So what's the derivation of this real quickly? You can use a basic energy derivation of the rotational inertia for a small chunk. Small chunk, well, when we do these kind of approximations, there's two ways to think of it. One is, in my application, I don't really worry about certain details because it doesn't affect my result enough to worry about it. In that case, small would mean small, usually compared to R. How small? Well, it depends on what you're doing. So it's the size of the object is small compared to the radius of the rotation here. Think of this as a rotating object on a string. The other way we think of a small chunk is in the limiting case using calculus, where we make it smaller and smaller in the limit, and we use methods of integration or differentiation. So it's really simple. We just remember that from rotational kinematics that tangential speed, is r omega. Right, r omega. So you can check the units meters per second, meters, radians per second. Okay, so that works, and that means that the kinetic energy of this ball is 1/2 mv squared, which that v is the v for speed tangential. Okay. Initially, here we're not going to let the radius change. That just adds more complexity. So we're just going to go with this case here. 1/2 mv squared. Well, a v is r omega, so I'm going to replace v with r omega. So I haven't done anything different. I just put it in terms of rotation. So there's that. And then I'm going to regroup it. So now I'm going to pull out the mr squared omega squared, so that I've taken my old equation 1/2 mv squared and written it in terms of rotational things, 1/2 I omega squared. And you can see here then that I, or rotational inertia, has units of, say, kilogram meter squared, or mass times any length squared. That's the units. Why? Because it works. It's an invention, right? It's a nice way to keep track of rotations. Okay, the old physics works. So let's go over here and see how we do this. We come up over here and we say, all right, we got kinetic energy of rotation is 1/2 the rotational inertia times the angular velocity squared. 1/2 I omega squared. It's a lot like 1/2 mv squared. And the beauty here is, since it came from 1/2 mv squared, this is going to be in units of, say, joules. It's still joules, so we add it into the rest of our energy equation. It's just another type of energy. It's another ability to change things. If something's spinning, you stick your hand in there, ouch, it can change things. Okay, cool. So what we want is the rotational inertia, a moment of inertia, of a small chunk. We're going to build that up. We did the derivation here, so just remember it's mr squared. Okay, why? Because of you connect it with 1/2 mv squared. So just keep that fresh. That's why. It can seem abstract, but it's not so. Or for a very small chunk in the limiting case, we say dm. So d is not delta m, it's dm, which for physics we'll use this. You'll use dq for electrostatics for a little bit of electric charge. And mass, of course, is a property. So dm of a small chunk times r squared. Or if we want, we could write that r squared times dm. It doesn't matter, we're just multiplying, it doesn't matter the order. So we've got that idea. So there's 4 ways to find the rotational inertia of an object, of this object, or of this object, or of this crazy object on the side, or anything. One is by experiment. So you can just simply measure, how much something's accelerating and use this calculation. Do an energy analysis is usually easier. You can do a torque analysis, which is a Newton's second law for rotation too, but you can do it by experiment. So that's a good thing to do. If it's a weird shape and you can't really characterize it mathematically, you can do it by experiment. You can put it on a piece of apparatus. and you could have a nice method. The other way mathematically is you can add up the I from each little chunk. And it just adds up. So the total rotational inertia of the object is the sum, which is the Greek capital sigma, or S, sum of the rotational inertia of each little piece, which is mr squared. M of A, R of A squared. M of B, R of B squared. So you need to make sure you see the axis of rotation and the object. The other way you can get it is look it up on a table. So this has lots of pieces, and it's not so easy, to do. That's kind of weird. This guy has this chunk and that chunk, but then it's also got the rod, and it's got these guys here too. Like, what's going on with that? So I can rotate it around this axis. But it depends on which axis you're rotating it around. So be careful, because if you look it up on a table, they'll specify which axis you're talking about, which axis of rotation. So you can look it up on a table, and that's what engineers often do. It's important to have an intuition for what rotational inertia is when we look it up. How do you get it on a table? Because in a table, it just gives you sort of a special cases, uniform density, nice perfect shapes, and so on. So how you get that on the table is to integrate. And again, this technique is more important than just for this case. You could look this up on a table, but there's lots of ways in physics that we integrate. So it's not bad when you get the hang of it. What's the total? Well, it's the sum. Now we use not the choppy Greek sigma, but now we use a Roman S for summation. Okay, that's where the integral sign comes from. And we're going to add up all parts of the object. And this dI is the rotational inertia of any one little chunk. And then we just add it up. So this is really the same. If you get this idea, you get that idea. You're just using better notation, calculus notation of a small chunk. Now you need to make it specific, because this isn't any good unless you make it specific. But if you can write it generally, you're in good shape. So we can start here. Don't skip that step. And then dI, what's dI of a small chunk? Well, it's r squared dm, or dm r squared. It doesn't matter which way you write that. Remember that when you have an integral, you're summing it over some pieces. So you're summing over that. Okay, so that's it. Now we got to make that specific. So to make it specific, you've got to do a few steps. Obviously, you got to choose your object and sketch it, right? You need to choose your axis of rotation and show it on your sketch, right? So that's very important. Is this your axis of rotation over here? Right? That rod would be your axis of rotation. Then R would be from each piece to that axis. Is this your axis of rotation? Then it's going to be a different answer. It's the same object, but you've got a different rotational inertia for different axes. Same mass, same shape, but if you're trying to rotate it around a different axis, you're going to get a different resistance. Okay, so that's what we're going to calculate. Kind of cool. It's really amazing, powerful. So to make it specific, choose your object. You got to know which axis of rotation you're going to use. Then 1, 2, 3, 4. Check it out. We're going to do this way. 1. You need to sketch dm. That is a little chunk. Now dm needs to be a general place. So if I'm doing this rod, which is a great example here, around this axis of rotation, I'm not going to choose the center, I'm not going to choose the end, I'm just going to put it somewhere. Because I'm going to add them all up. Once I can write an equation for the I of that little chunk, the dI of that little chunk that has mass dm, then I can use my mathematical crank and figure out what the summation of the dI of every little piece is, and I'm done. That's all you have to do. So it's very general terms. We need to make it specific to help it sink in. But that's, if you write this, this will tell you what to do. 1, 2, 3, 4. This is how we're going to do it. 1, 2, 3, and back to 4. Okay? So 1, just sketch a DM. That's very quick and easy. Show it on your picture. Always show it on your picture, it gets too tangled. Fine. 2, what's R of that chunk? What is that R? Well, it's something you're going to sketch from the axis of rotation to dm. From the axis of rotation to dm. Now let me show you an example here that can be maybe tricky. Suppose this is my axis of rotation. And suppose my object is like this. Now this is kind of a fun one. Okay, and it's attached here, so the thing spins around like this. Then I don't overthink it. Don't think too far ahead because you'll get stumped. Just go, I don't know, I'm going to get some partial credit here. I'm going to take a little piece somewhere. Here's a little piece right in there. It's got mass dm. And let's see, where is R of that chunk? Does it go down to here? From there to the axis? Wait a minute. What I mean by that is the circle that is making is this, because it's spinning around that axis like this, and so R would be here. Okay? And you could write an equation for that. So some of the difficulty, when the difficulty becomes the geometry, then you've got the basic idea. And you might have to write an equation for a line, or an equation of a circle, or whatever the curve is, or whatever the shape is. But you know how to do it. You just got to work on your geometry. Everybody cool with that? Good. So, all right, so this tells you what to do. It's a cheat sheet, right? You can't bring notes into the exam. That's okay. You can write this and you got your notes. Find dm, show it. Then R. Oh, we've already shown the axis of rotation. It's from dm to the axis of rotation, but the shortest distance, right? Cool. So I sketched that. Fine. Then you're going to have to put it in terms of your coordinates. And this is the part of the geometry that can be a little bit tricky, right? In more complicated cases. In this course, often we'll do a simple case. But what is that in terms of coordinates that you might be using? Okay, so that's the specific. Now let's go here. We've got steps 3 and 4 to do. What are the limits of the integration? Well, the limits of the integration would be the range of all R for all parts of the object. In other words, we're going to sum up the DI, the rotational inertia, for every single piece. And this picture over here that I was working with, right, we had that, we had this axis of rotation, we had some rod here like this at some angle. We looked at a general piece that has mass dm. It's going to make a circle around here so that the R is there. Fine. But the limits of integration, that's the R for that dm. I need to sum up every single piece, right? And then I'll get the total rotational inertia of that object. And how do I do it? By integration. So the range of the R would be from here, 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 here. And of course, we like calculus. Once we set it up, generally we set it all up. And so we have to integrate over all pieces of the object. Okay, and you'll see again when we get specific, it's not so bad. But again, remember this. Remember that the integral is 1, 2, 3, and now we need 4. Because how do you integrate dm over coordinates? What's R got to do with dm? And it doesn't really yet. So you've got to transform dm into something over, say, dx, or dy, or dz, or rd theta, dr, or whatever. It's just geometry. The physics here, though, is here. But we've got to sum up every single piece. So the way we do 4 is we put dm in general in terms of the coordinates by using density. Right? We're going to do this for center mass as well. And in fact, we're going to use this for electrostatics, where rather than mass, we use electric charge. Okay, cool. Let's define density correctly. Density and dm. The general definition that I like to give for density is it's the amount of stuff or property. So it could be how many ants, how many dogs, how many shoes, whatever. Or how much mass, how much electric charge, you know, whatever it is. Divided by the space occupied by that stuff. Now the space could be a volume, an area, or a length. Now it's true that objects in 3 dimensions in our space occupy 3 dimensions. This ruler occupies 3 dimensions. So if I look up the density for wood, I'm going to find the mass per volume of wood or iron or whatever it is. However, if I've got a shape here where the cross section is uniform, so that area is the same, then I know if I cut 1 centimeter of this meter stick, I'll get a certain amount of mass. So if you gave me the mass per centimeter, I know what that means, that if I cut 1 centimeter of this stick, I get that much mass. If I cut 2 centimeters, I'd get 2 centimeters times the mass per centimeter, times the density, right? Okay, so you can use mass per length even though we know that it occupies 3 dimensions. Okay, so bottom line is, if it's more dense, it means you have more stuff packed in, or you take the same amount of stuff, like a squishy ball, and squeeze it into less space, right? It's more packed in. So more packed in, more squeezed in. That's what density is. And it could mean anything, right? How many ants are in a line that are invading your house? How many ants per inch on a line? How many ducks in a row? How much stuff on a table? So you can talk about how much ink per area on this board, whatever you do. Okay, cool. So mass density in particular is the amount of mass. That's the stuff we're talking about. That's the property we're talking about over the space occupied. So let's take a look over here and set this up. We'll get specific on the next one. Density, in general, can be written as mass per volume, mass per area, mass per length. Some books use different notation. This is a pretty common notation, but some books will use different notation, and you just get used to it. It's pretty common. For mass per volume, we use the Greek letter rho. It's not P. It's important not to be sloppy. So it's kind of this little curved, looks like a P, but it's rho, and it's actually pronounced like an R in Greek. This is the lowercase sigma, which is a circle with a little flare, flat tail to it. And this is the lowercase lambda, and it's like an X without the upper right part, and often we curve it and give it a little flare too. Lambda. These symbols can mean a lot of different things. In this context, it means this: mass per volume, mass per area, mass per length. In general, it's the mass of a little chunk divided by the volume of that little chunk, or the mass of a chunk divided by the area, if we just care about the area, or the mass divided by the length of that little chunk. In general, that'll be true, because the density could vary throughout the object. You can have parts where it's more dense and parts where it's less dense on the object. But that's generally going to be true for every little piece. And then you might have an equation that you're given for each of these. So you throw it in the integral and do it. But in the case where there's uniform density, then that is equal to, and you have to know, the total mass over the total volume. Just take the total mass divided by the total volume, and that's the density. Or total mass over total area, or total mass over total length. Okay? But you can't use this if this is varying. If this is varying, you need to be given an equation that's been used to engineer the thing or whatever it is. Okay? All right, cool. Now, so, how are we doing? All right, so figure out what dm is. What's dm in each of these cases? It's going to be rho dv, isn't it? It's going to be sigma dA. It's going to be lambda dl. And now we need to make it specific, and let's do some examples next.